If the encoder and decoder have agreed upon ahead of time a scheme for chopping in half that uncertainty volume, that volume where you don't know where the state is, and labeling one with a 0 and the other piece with a 1, the two symbols here, then the encoder will send across this one symbol here, because it's in the 1 region, and suddenly the decoder gets that symbol and knows that it doesn't have to worry about that other piece of the uncertainty volume. So it can now then focus on trying to drive this whole set, sort of to the origin. And this can repeat, so this will grow into the process. It'll be another transmission time. Hopefully it'll chop it in half. And this whole thing continues. And the basic idea behind this inequality is the left-hand side is how fast are you chopping that uncertainty volume in half? The right-hand side is how fast is that uncertainty volume expanding because of the unstable eigenvalues of the process. And if you can chop it in half faster than it will double in size, then on average you can stabilize it. That's the underlying idea behind this concept, behind this inequality. So now let's expand this problem a little bit. We'll ask a new problem. And we'll motivate it with the following idea, the following observation. That the absence of a transmission, of a symbol, the absence of an explicit transmission still conveys information, and it costs no energy. If you and your friend agree to meet at the coffee shop at 3 p.m. and your friend doesn't show up, you don't know exactly what happened, but you know that still sends a signal. Maybe he slept in, maybe he's watching Netflix, maybe he doesn't like you anymore. There's some sort of signal that is getting across there. You see this on Facebook. Okay, so the absence of a transmission still conveys information. Let me give you an example of how that might be used to facilitate communication here. So this is our normal communication setup, and let me imbue it with some actual agents. Here's a robot that is trundling around on the ground trying to achieve some sort of control objective. And it has a radio that it can power up, pump some energy into, and send some information about the state of the robot. The robot has a finite battery, so this takes a little bit of energy to do that, and you don't want it to run out of juice. There's some big mainframe that can receive all of this data about the robot, and it has some big powerful antenna that it can beam an actuation signal to the robot. And so there's sort of an asymmetry here. The robot has a tiny little radio. It needs to conserve energy. The mainframe can blast it, essentially a continuous time real signal to the robot. And here's an idea for communication. The robot and the mainframe might decide this. Every second, the mainframe is going to expect 1 bit to come from the robot. The robot's going to send 1 bit. Could be 1 or 0. Let's say it's 1. It's going to send 1 bit. It's going to send a 1 bit to the mainframe. Where that happens in time, in that 1 second, is going to provide all the information. So here's my 1 second interval. Chop it up into 1,000,000 pieces. So there's 1 microsecond little bins where that 1 bit could arrive. If the clocks are synchronized, so you can actually send this at a microsecond granularity, when that bit arrives, the mainframe will look to see which microsecond did it arrive at. There's 1,000,000 microseconds that 1 bit could have arrived at, and 1,000,000, if you take the log base 2 of that, is about 20. So that's, if you number these microsecond wide bins, there's 20 bits of information in which microsecond that bit arrived in. So the robot sent 1 bit, but it was able to convey 20 bits of information in the timing of when it received it. So this is kind of a weird idea, and this is what we are going to formalize and explore. This idea that you can, in a sense, you can use the timing of the bit to convey information instead of the content of the bits, which is how it's normally sent. Okay. And of course, the goal here is to send as much information as possible in the absence of a transmission, in the quiet time. When the radio is off, that's still sending information. How can we leverage that to send the most information possible in that silence where we're saving battery power? So here's the setup that will let us do that. Here's the framework that will let us formalize that. As before, the encoder will transmit symbols from the alphabet 0 to S, just like before. And now we're going to assign sort of a cost to these symbols. We're going to say the 0 symbol is free in the sense that it does not consume any communication resources to transmit that 0 symbol, but every other symbol in the library consumes 1 unit of communication resources when you want to send it. So it takes 1 unit of energy, say, whatever your communication resources are, to send symbol 1 or symbol 2 or symbol 3 or so on. But if you send symbol 0, it doesn't cost anything. It's essentially 0 is the no transmission symbol. It's the symbol that gets sent if the radio is turned off on the robot. With this idea, we can define the average communication of an encoder, of an encoding scheme. We say that an encoder has average communication not exceeding gamma if for any symbol sequence that it might send, the following inequality holds. This is kind of a weird inequality, but what it is this is saying take that symbol sequence, any symbol sequence that that encoder might transmit, and look at some window within that symbol sequence, starting at n1, wherever you want, any n1 you want, and with a width n2. If you look at a large enough window, a large enough n2, and you ask yourself, what is the fraction of non-free symbols, of non-zero symbols in this window? So how many 1s and 2s and 3s and 4s and so on are there? Like discount all the zeros. You can ask, what is the average cost, the average cost per symbol in that window? And what this is saying is, if an encoder has an average communication not exceeding gamma, where gamma is some number between 0 and 1, then anywhere you look, any window you pick, if you look at a large enough window in that symbol sequence, the average cost per symbol will be less than gamma. So if somebody says, please make me an encoder that will only transmit less than 70% of the time non-free symbols, what they're saying is essentially they want the radio to be off 25% of the time. And the 75% of the time that's essentially a maximum bound on any symbol sequence that you look at, so provided that it's big enough. So that is sort of this key idea where this gamma here, this average communication is sort of a maximum fraction of costly symbols used by your encoder. Okay. So in the old days, the Tadikonda, Mitter, Nair, and Evans result that people love answered the question, what are the conditions on the bit rate and the system matrix in order to stabilize the system? And it was this inequality. What we ask now is, suppose in addition to having this bit rate constraint, you also have this power constraint. You say, I need you to stabilize the system using 100 bits per second. And by the way, 70% of those have to be 0, have to be the 0 bit, the free symbol. What does this additional power constraint do to your ability to stabilize the system? That's the question that we ask, and that's where we're at now. We're going to talk about the new necessary and sufficient condition. So it's this. It's a necessary and sufficient condition. It's the same one as before, as the Tadikonda, Mitter, Nair, and Evans. There's just there's a new term here. So as before, the bit rate has the same definition. And this f function, you can think of as sort of a penalty function. It has kind of a weird form. I'll plot it for you in a second. But you can see that it's 1. So this is always going to be less than 1. You'll see in a second. And it's 1 when gamma, the average cost, is high enough. When it's in this top little region here, the penalty function is 1. Otherwise, it's always less than 1. When it's less than 1, that's bad. That has the interpretation that if you have some system, somebody starts imposing a power constraint on you, and it's less than 1, your bit rate has to get bigger in order to compensate for that power constraint being less than 1. If it is 1, that's saying that there is essentially no penalty for that power constraint. You do not have to have a higher bit rate in order to compensate for the power constraint. Okay, so let's look at this thing and we'll talk about a couple of consequences. I'm sorry, yes, and this h here is the base 2 entropy. This is like the entropy of a Bernoulli random variable. Like a biased coin has this entropy every time you flip it, and it has this sort of nice little hump here that you might have seen before. So there are two observations to make with this inequality. The first one is that if an encoder stabilizes the system with a given bit rate r, then you can make a new encoder that stabilizes the same system with the same bit rate, but it uses an average cost of a half. And that is saying that so somebody comes to you on the street, they say, hey, great news, I can stabilize the system and with only 100 bits a second, and you can say back to them, I can stabilize that same system with the same bit rate, but my encoder will be off half of the time. This is a very counterintuitive thing, because you would think that if somebody starts imposing a power constraint on you, like you have to build an encoder that is off 10% of the time or is off 20% of the time, that would mean that you would necessarily have to boost up your bit rate. You would need a higher bit rate in order to compensate for the fact that there were essentially, by imposing a power constraint, there are going to be certain symbol sequences that you are not allowed to send. You can't send a string of ones because it's too expensive. You have to have 80%, you can only have 80% ones or something. The reason this is the case is because this f function here is 1 at very high value, well, at high values of gamma. When the power constraint is high enough, then there is no penalty here. So this is this f function for a few different sizes of alphabet, and you can see that the highest the f is, which is sort of the best, most favorable configuration, is when there's only 2 symbols, 0 and 1. And in that case, you can penalize your power constraint all the way down to 50%, and it will still stay constant. It'll still stay at 1. That seems like great news. The downside to this is that you don't get this for free. The encoders that you end up producing when you impose a stricter and stricter power constraint turn out to be more and more complicated. They use longer and longer code words. They have longer and longer bit strings. It takes longer for them to send all those code words across the channel, and so your performance doesn't actually, the state will end up getting very big before you get a very informative symbol, and then you can shrink it down again. So you don't get this for free, but that sort of turns into an implementation problem. The second observation is that you can stabilize any system while using an arbitrarily small average power. So the average power is not the same as the gamma, not the same as the average cost per symbol. We're talking about the average cost per second. This is sort of a more natural thing to think about. Somebody might say, please stabilize this robot and it's only allowed to energize its antenna 4 times per second. And that, if you transmit at constant periodic intervals, then the average power is just gamma over t. So this is the thing that would be, you want to be less than 4 times per second or something. So if you have a power budget and you have this stability criterion, this is the same condition as before. I just plugged in the definition of R, roughly. There are 2 ways that you can satisfy both of these simultaneously always. One of them is to use a large alphabet and a large sampling period. In other words, only send once every zillion seconds, but when you do send a symbol, it will come from a very, very large symbol library. And that symbol library will be so big that it will contain a lot of information. Every symbol in there will contain the log base 2 of the size of the library. So it'll contain a lot of information. You just don't get it. You just don't get a symbol very often. So you're not sending very often, so the power budget's very small. And we show in the paper that you can crank up the size of the symbol library in order to make this always satisfied, even if this is a very large number too. This essentially corresponds to sending very informative symbols, but you only get to send it once in a while, and so the state kind of gets very big before you constrict it down again. And it's very complex. If you use a large symbol library, the encoder and the decoder have to have those symbol libraries stored in memory, and it's kind of a pain in the neck. The other way to do it, which is more interesting, is to have a small sampling period and a very small average cost. So the idea here is, if you have a very small sampling period, what that means is that the encoder is sending symbols very, very, very quickly. You would think that that would be an expensive thing to do, but if you turn down the average cost a whole lot, that means that most of those symbols have to be the 0 symbol, the free symbol, because with a small average cost, that means that most of the symbols have to be 0. So this is capturing the idea that I talked about before, where if you have 1 second and you chop it up into 1,000,000 pieces, and you say, you're gonna send 0 for all those 1,000,000 pieces except for 1, that's a situation where you have a very small transmission period. You're sending, this is a microsecond. This is the bit that you're gonna be sending, either not sending at all, that's a 0, or sending a 1 bit. And most of them, almost all of them are 0. You're almost always sending the 0 bit, no transmission. So this is how we formally, this is the situation where you're sending information in the timing of the messages rather than the content of the messages themselves. So in order to do this, obviously, you would need a very precise clock. You need to be able to say, I got it at microsecond number 1, 2, 3, 4, 5, and that is actually the microsecond that was intended by the sender. So you need to have synchronized clocks in order to do this. Okay, so The summary so far is that we took this bit rate constraint, this necessary insufficient condition from Tadikonda, Mitter, and Evans, and we expanded it to include this idea of an average cost, essentially a power constraint on your encoder, and that ended up resulting in this funny sort of penalty function that has some interesting interpretations. Next, let's talk about how this can apply, to event-based encoding. So the encoders that we developed here had this problem that I sort of referred to. They have these big symbol libraries, and that can be a pain in the neck to implement. Maybe there's a way that we can not implement them. We can implement a simpler scheme that will be easier to implement, and hopefully it won't be too suboptimal. And that's what we'll talk about next. So a lot of folks have worked on event-based control before. It's been known for a long time that that there are resources to be gained if you only have the controller, or if you only have the sensor send its messages when some sort of event-worthy thing has happened. So the robot is trundling around, it goes outside of some sort of safety zone, then you should start sending messages. But as long as it's doing its normal thing, it's acting appropriately, you don't need to consume communication resources to convey that. Andy Thiel and Dragan Nezic have worked on this. Yeah. Good job, Andy. All right, yeah. And Paulo Taboada has done work where if you have like a nonlinear system, you might worry that you're going to have a whole bunch of events fire right after each other. You're going to have sort of like Zeno type behavior. And in Paulo's work, he can establish that there is going to be a finite gap in time between two events, so that'll help prevent that. And so a lot of people have worked on event-based control. And our setup is going to look like this. We're going to use what's called an emulation-based controller. So in the good old days, before there were communication constraints, if you had you could design a state feedback controller where the controller just gets to read all infinite precision bits of the state and use the control law U equals kx. That control law is not going to work here because you have a controller, because the controller doesn't get to know the actual state. It only gets to know these symbols. So here's an idea. Let's have the encoder and the decoder send symbols in such a way so that the decoder can maintain an estimate of the state, and then the controller will apply the feedback. It's not true feedback control because it doesn't have the state fed back, but it will use the same feedback gain, k, times x hat, the estimate of the true state. So that's the idea. This is an emulation-based controller because it's pretending to be that it's state feedback controller, but even though it doesn't have the state. And this will be event-based in the sense that the encoder will most of the time be sending 0. It'll most of the time be sending the 0 free symbol until there's a big difference between the state estimate and the true state. When there's a big difference between those two, that's worthy of an event. That's worthy of spending some resources to tell the decoder that it needs to correct its state estimate. And so that's why it's called sort of event-based. Most of the time it's sending 0, except when the state estimation error gets too big. So let's talk about how to build this. Inside the plant, there's dynamics, like we know and love. The encoder and decoder contain a copy of the dynamics, the so-called auxiliary system. This is the state estimate, this x hat. And because the encoder has access to the dynamics, it can read the state, and is running a copy of the dynamics that it shares with the decoder, it can compute the difference between x and x hat, and this is the estimation error. It's essentially the difference between x and x hat, and there's this time-varying coordinate transform that's based on the real Jordan normal form. And this essentially serves to decouple the A matrix, essentially decouple the components of the estimation of the state estimation error into a bunch of pieces. So for every one of the Jordan blocks in this decomposition, there is an error component. So if it's a nice diagonalizable matrix, then this is just the size of the matrix. This is a scalar. There's just one error in each dimension between the state and the state estimate. And you can choose this P, this coordinate transform, such that every one of these little error coordinates evolves essentially exponentially. There is this matrix here that is kind of a pain in the neck that has to do with the multiplicity of the Jordan blocks. If the Jordan blocks are real big, then this thing is full of polynomials and t. But the whole thing is dominated by this exponential So what this is saying, this is the most technical slide in the talk. What this is saying is the estimation error will grow essentially exponentially inside between two transmission times. And this is the thing that we're going to be, that each encoder will be monitoring. We're going to have a bunch of encoders. How many Jordan blocks you have, we're going to have that many sub-encoders. Each one is going to be monitoring its component of the error. And when that component of the error gets too big, it's going to send some symbol to the decoder to correct it. So here's how it works. We'll just look at a scalar case, for example, and then the multidimensional case will follow pretty easily from that. So initially, the error is at some point here. It's in this. We choose this box, this minus L to L box, to be sort of a safety box that encloses the initial uncertainty set where the initial condition lies. And this estimate, error, this state estimation error, will grow at, as we were saying before, essentially exponentially. So at the next sampling time, it will have grown and maybe have grown outside of the box. If you're lucky, it's very close to 0, and so it doesn't even leave the box in one sampling time. But maybe it does. Maybe it leaves the box. In that case, now it's between L and L e to the AT. This is the biggest it could possibly get, even if it had a whole capital T seconds to grow from L out. So it'll never go farther than this. Now, it's a sampling time, so the encoder gets to decide what symbol to send. It's in the 1 zone. It could be in the -1 zone. That would mean it left out the left-hand side of the safety box. And so the encoder, yes, and this is how big it could grow if it had the whole T seconds. So the encoder will send a 1. It sees it's in this zone, so it decides to send a 1 over to the decoder. The decoder then incorporates that into the state estimate. It says, aha, I see that the thing left out the right side of the box, so I'm going to update my state estimate with some correction term. What correction term? How about the midpoint of the box? If you use the midpoint of the box and you add that to your state estimate, that will change the state estimation error in a favorable way. What it will do is it'll shrink the state estimation error and move that blue box down until it's re-centered at 0. And you can see, this is like a nice geometric argument, it's more formal in the paper, that if this region here, this blue box here, fits inside the -L to L box, then the situation can just repeat. Then you've got the error back in the safety box, and you get a whole nother T seconds to think about whether it'll stay in the box or whether it'll leave. So in other words, if this region here fits inside here, then this scheme will bound the error, and it'll bound the process, the state of the process. So what I just said about the blue box fitting within the -L to L, you can formalize that and essentially manipulate it and show it as this condition here. The condition is, if this looks a lot like the Teddy-Kahn emitter Nair-Evans thing, also looks like the other necessary and sufficient condition that we cranked out, but there's this new term here, this sort of H inverse of gamma, and there's the log 3. And if this condition is satisfied, which is a weaker condition than the necessary and sufficient, like minimal, theoretically possible bit rate condition, then this scheme will use a bit rate less than R, use an average communication less than gamma, and bound the state of the process. So this, so something that we might be interested in is, so where do we start, where do we end? We started with this stability condition. We added the idea of this power constraint, and then we said, let's see if we could, how good is this event-based controller? And if you look at essentially the ratio between this bound and this bound, you see that this one is greater than it. It has to be greater than it because this is like the minimum possible necessary and sufficient condition bound. So this one is greater than it. It is a sufficient condition for the event-based controller to stabilize things. And it's about 2.5 times bigger than this one. So if you look for all gammas, all possible power constraints that you could put on, this will never be bigger than 2.5 times the minimum possible one. And that means that if you are designing a system, and you look at your minimum possible, you look at your necessary and sufficient condition to see if I stabilize it with this bit rate and I impose this power constraint, I use this big of a library and I have this system, and it's satisfied. If it's satisfied so that you could reduce this by a factor of 2.5 and it would still be satisfied, that means that this will be satisfied for sure. And that means that this event-based control scheme will stabilize the system. This event-based control scheme is much, much, much easier to implement than the complicated kinds of controllers that you get from this theorem here. So what this is saying is, if you have a little wiggle room, save yourself some trouble and use an event-based scheme. That's really That's pretty convenient. I sure would like to be able to use an event-based scheme instead of this complicated thing. Okay, so that is the end of this part here. The point of these two things is timing can have many benefits in network control. We talked about this thing with the 1 microsecond, and there's a million pieces in it, and if you have precise timing, you can identify, you can send seemingly more information than you should be allowed to by just with the timing of the packet. Let's now look at a situation where you don't have a network control system. You don't have to send symbols around a network. You're just looking at a single local system.